Hello and welcome to this machine learning course. I am Ludwig, and in this first lecture I'm going to cover some more bureaucratic aspects of how the course will work, and then I'm going to talk a bit about what machine learning is and for what it can be useful. Then we'll see the objectives of this course and the outline of the subject matters we are going to cover. Then we'll take a short break, and in the second lecture after the break I will cover the beginnings of supervised learning, and we'll start seeing regression as an example of supervised learning. So we'll divide these 2 hours into two blocks with a short break between them. So first, I will give these lectures, so the theoretical part and also the tutorials P1, P5 and P6. Professor Joaquim will handle the other tutorial classes. You have the more information and class planning on the course site. Note that the planning for the tutorials may be changed a bit because of this initially unforeseen delay in how in the timing of the lectures. But in general, you'll have the planning there. You'll have access to the slides, the lecture notes, and also the links to these videos. So after streaming, the video will be available on the YouTube channel if you want to see it later. The classes will be 2 hours of lectures per week, so I will divide these into 2 lectures, and I'll try to keep them shorter than 1 hour, even with the break, so that we have some time at the end of these 2 hours for discussion using the Zoom meeting. So if you have questions or if you want to talk to me about some of these subject matters. Then the tutorials, you also have 2 hours per week. These will work in Google Hangouts, and they are meant to help you solve questions or difficulties with the exercises. So what I suggest is that you try to do the exercises. You have the tutorials planned out in the course site, and you have a PDF with the different exercises for the different tutorial classes. So if you try to do the exercises, then you can bring your questions afterwards, and we can address those. If the exercises are too easy, you don't need to attend the tutorial classes. So the tutorials are meant for clarifying questions that you may have. There will be some lectures reserved for revisions and for help with the assignments too, but these will be in the planning. So for the assessment, there are 2 parts, the theoretical and the practical parts. The theoretical part is composed of 2 written tests or a final exam. These will all be online, so you have questions with long answers, and they are timed. You have a time limit for each question. The exam will be scored into independent parts, one corresponding to the first test and the other corresponding to the second test. So if one of the tests does not go well, you can take the exam only for that test and retain the score of the other tests that went better. The assignments, you'll have 2 assignments along the semester. They will be done in groups of 2 students. Ideally, they can be in the same class, but this year it's not a constraint. So if you need to partner with some colleague from another tutorial class, it's okay, or even another course. So this is merely a recommendation, but it's not a constraint. However, for the assignments, you not only have the grade for the assignment, but this grade will be modified according to a specific question about the assignment that you'll answer during the test. So there may be different variants of the question for different students, and this will be a more individual evaluation for each student. So I recommend that you form groups by October 18, and all the submissions for the assignment should be to that address, Prática DCE, which is used only for automated processing. So all the submissions and for forming groups also, I will post the instructions online, but you should always send emails to that address using your official FCT address so that I can identify you automatically. For the final grade, you need to have at least 9.5 out of 20 in each component, so the theoretical and practical component, and the final grade is the simple average of the two components. If you have the practical part from previous years, from 2016 onwards, you should not enroll in practical classes and in the tutorials, and you can retain the grade from those that year. So we will be using Python 3, and I recommend using an integrated development environment like Spider. If you want to use Jupyter, it's okay, but when submitting the assignments, you will have to submit the Python source code, so simply the .py file, not a Jupyter notebook. Also, I do not recommend Jupyter because it encourages quite messy code, as you tend to copy the cells and things like that instead of structuring code in functions. We are going to use several libraries like NumPy, Matplotlib, scikit-learn, and so on. So the simplest way of getting everything you need for this course is just to install Anaconda. This is a free distribution, and you have there the link, so you can download it and it will install all the libraries that you need. I provide lecture notes, so summary of each lecture on the course website. You can use this for studying, and also I recommend for having a bit deeper explanations, often deeper than what we cover here. I recommend Bishop's book, Pattern Recognition and Machine Learning. There are other books that those other three, I'll often refer to them because it may be useful for you to see things explained in different ways. It may help understand some things. That would be the purpose of Alpiden and Marsland's books. Mitchell's book is mostly a classic on machine learning, so I'll refer to it a few times, but these are not that important for studying. So the first two items there on the list should be the most important ones for studying for this course. Okay, so machine learning. The basic idea of machine learning is actually quite old, at least old measured in the field of computation. So we have this idea from 1959 that we could give computers this capacity for learning how to do things without having to tell them exactly how to do those things. So this is the idea of making the machine learn how to perform some task. Mitchell formalized this a bit more. So this definition says that we can say that a computer or computer program can learn if giving it this experience, E, which can be, for example, examples of what we want it to do. We can measure some performance in some task, some specific task, and we have a measurement of performance, and the system is learning if its performance at those tasks will increase as we give it experience. So this is a more rigorous definition of machine learning. It's a computer program that can improve performance at some task as we give it more examples, more experience in solving that task. So basically, to have a machine learning problem, we need to specify the task that we want the system to perform. We need to have some way of measuring its performance, and we need to have this experience, so the data that we are going to feed into the system in order for the system to improve its performance. So basically we need these three things so that we can specify a machine learning problem and get the system to learn. For example, this is from a paper that's trying to automate flight ticketing. People can telephone the flight operator and ask things like the schedule for flights between some cities, or information about ticket prices, or make reservations, and so on. So what the system must do is have something to convert from voice to text, and then analyze the text and identify different parts. And the data that they use to train this system is a set of annotated voice records. For example, this "please book me on" is annotated as referring to the act of booking a flight. This flight 21 is the number of the flight, and so on. So if we have a set of records where we annotate what each fragment corresponds to, then we can feed that into the system as experience, and the system hopefully will start to learn how to annotate new examples correctly by identifying the right fragments. So with this kind of approach, we have many different problems that we can try to solve, like predicting prices. This would be an example of a regression problem, which is trying to predict some continuous value. Classification problems, like classifying spam emails, where we are splitting our examples into different classes, and then things like trying to figure out what people purchase together. So for example, if people buy baby formula, probably they will buy diapers too, and so on. Grouping similar things together, which is clustering. We're also going to look at that, and so forth. So there are many different problems where we can, based on a set of data, put the computer to learn how to organize things, how to give the correct answer, and so forth. So basically learn to perform at some tasks that we specify. This is a field that is related to other disciplines, so naturally computer science, but also you have lots of statistics and probability, and I will focus quite a bit on these aspects of the underlying statistical and probability formalities on the methods that we're going to use. Mathematics in general, also for numerical computation, for the optimizers and so on. And then there are lots of implications. There are approaches to machine learning that are inspired by neuroscience. There are some sociological and philosophical, ethical aspects to machine learning, and so on. So basically, this is not something that is isolated from the rest. We need to think about it in the context of many other areas. So what can we use machine learning for? Basically, the most useful application of machine learning is to solve problems for which we do not have an explicit solution. So we cannot specify a set of rules that can solve that problem. One example is identifying handwritten digits. So we can easily identify that this is a 9, this is apparently a 6, 2, and so on. But if you needed to write a computer program specifying the detailed rules on how to identify handwritten digits, it would be very hard, or probably even impossible, because we cannot make explicit the kind of operations we are doing when we are identifying numbers. So in this case, if we cannot create those explicit rules, we need to find a way for the system to learn by itself the patterns, the regularities in the data, and try to find the correct answer. So the idea here is to train with labeled data. We can identify each digit, for example, by labeling using humans to label them, and then have a data set. And then we need to find some function, some way of mapping between the images that we get and the correct answer that we want in the labels. And if the system increases performance in that task as we feed it more examples, then we can say that the system is learning, and that would be an example of machine learning. So in some kinds of tasks, we may not need to have labeled data. For example, for clustering and so on, we're going to see that kind of problems too further on in the semester. But in some cases, if we have a target that we want the system to predict, then we need to feed it with examples that already have that target, so that the system learns to map between the input and the output. Machine learning is also useful when we have large volumes of data and we need to process it quickly. Sometimes we can write explicit rules to do some operations, but they may take too long. If they are very efficient, then they can be a way of solving the problem. But if they take too long, or if we don't have those explicit rules, then we can use machine learning. So, for example, Google searches, Facebook, when Facebook recommends posts and so on, also looking at the graph of relations of what things we clicked, what our friends like, and so forth, detecting or analyzing transactions, financial transactions such as credit card use to try to identify a problem. So these things that have to take into account huge volumes of data, they usually benefit from machine learning approaches. And also anything that needs to adapt quickly to different conditions. So if you have a system where human programmers have to write the rules so the system can respond differently to different conditions, and then the conditions change, you need to have the human programmers rewriting the rules all the time. This may not be feasible. But if you have a system that can learn automatically, then the new conditions will be fed into the system and the system will relearn and change its responses. And this is also, it happens not only in time, so you can have quick changes over time, but also in simultaneous. For example, with Facebook feed, the Facebook has different sets of rules, so to speak, to assign posts, so, or to feed into the post feed that each user sees, and these are customized, are personalized for the user based on the statistics of what kind of things the user likes and clicks and so on. So in order to do this individually for each of hundreds of millions of users, we need to have some automated system that can learn for each particular user what the user likes. It will not be feasible to have programmers writing specific rules for different users. So basically, machine learning is very good for tasks for which we do not have a recipe, or we don't have time to make up a specific recipe, a specific set of rules, if we have the right data. If we don't have the examples, that experience to feed into the system, then of course it will not work. Okay, so before we start looking at supervised learning in the second lecture, I will cover some basic concepts here for some terminology that we're going to use. So the hypothesis class is a set of possible hypotheses out of which we're going to choose one to for our system to use when we want then to ask for some answers. So basically, this is what we are going to assume about the solution to our problem. For example, suppose that we have this data set, we have blue dots and red dots. I'm going to use blue dots and red dots a lot during this course because it's easy to create two arbitrary classes and just represent them graphically. But suppose we want to train a machine learning system to separate red from blue. What we first need to do is to have some idea about what that separation will be like. And this would be the hypothesis class. For example, suppose that we will separate them with horizontal lines. We will choose a horizontal line that best separates the two groups. Now, our hypothesis class is horizontal lines because that's the whole set of things from which we can choose. We can only choose horizontal lines, so we'll choose one. And now we can create a model that represents this hypothesis class. For example, this here, which is y less or equal to some θ1, some parameter. So by changing this parameter, we can change the position of the horizontal line, and this parameter allows us to span all the hypothesis class. So this is another concept here. The hypothesis class is something abstract, the set of all horizontal lines. The model is an expression with parameters that we can adjust in order to choose an hypothesis from the class of hypotheses that we're considering. We can use another hypothesis class. So for example, circles of radius 1. In this case, our model will have two parameters, which are the coordinates of the center of the circles. And we consider to be blue everything that is below a distance of 1 from the center given by this θ1 and θ2 coordinate. So we can move this circle anywhere on this surface here and place it in order to separate blue from red. So this would be a different hypothesis class, all circles of radius 1. This would give us a different model. This model here represents circles of radius 1. And now we would try to pick the best hypothesis from this class by instantiating the parameters of the model. For example, -1, in this case, if we put -1 in this θ1 and also -1 in θ2, we have the circle centered here at this point. So basically, the hypothesis class is this abstract concept of the set of all hypotheses that we're going to consider, and the model is a representation of this set of hypotheses, of the hypothesis class, typically with parameters that we can adjust to instantiate each specific hypothesis. And the hypothesis will be one particular element of this hypothesis class. For example, this circle here is one hypothesis out of this class of hypotheses that we chose here. So basically, we can obtain one hypothesis by instantiating the model, assigning specific values to all the parameters. And this gives us one hypothesis. Now, the machine learning problem here, we can solve it by finding the best hypothesis. So if our system can learn, it will be able to use experience, use examples to improve by selecting a better hypothesis and eventually getting us a good hypothesis, or the best hypothesis ideally for our purposes. Now, one important thing here is that since we need to set our hypothesis class and then express it in some model, we are biasing all the process. So if we do it this way, we are assuming that we can separate the two classes using horizontal lines, and we are only considering horizontal lines. So this is a sort of inductive bias. We are assuming only horizontal lines will be part of our solution. In this case, it will be circles or something else. But this is the a basic notion here, that we need to restrict our hypothesis class in some way. Otherwise, we will not be able to predict anything new. So basically, the whole goal here, if we are giving examples for known examples so that our system can improve in performing some task, we want then the system to be able to perform this task on new examples that are outside this first set we used for training. But we cannot do that, we cannot go beyond the set of examples that we have if we don't assume something that restricts our hypothesis. In the middle of the semester, we will see this a bit more formally when we look at learning theory. But for now, I'd like to leave you with this idea that you cannot learn in the sense of being able to extrapolate from a set of known data to unknown examples if you don't assume something. For example, if we don't assume that gravity will still work tomorrow, then we cannot learn how to throw stones or use a bow and arrow or something like that, because we cannot assume that what we are doing today will still work tomorrow if gravity suddenly disappears. So this kind of assumptions that underlie the learning process is the inductive bias. And in the case of machine learning, the inductive bias is given by the hypothesis class that we're using, because that restricts the kind of solutions that we can find. Okay, so let's see some different kinds of machine learning problems. One that we're going to see later on in the semester, in the second part of the semester, is unsupervised learning. So in this case, what we want is to feed in to our system features. So features are the values that we can usually measure, easily obtain. And these will be the values that we have for all the examples that we meet. So we want to feed into the system these values, and then want the system to learn how to transform these values into new features that are more useful. So one example of this is clustering. In this case, we are clustering similar images. So this clustering method in this paper uses not only measurements, features taken from the images like colors and shapes and so on, but also metadata taken from the pages where the images are. So for example, you can see here Pluto the dog and Pluto the planet. They are clustered together, but they are also clustered with images of similar color and so forth. So this is an example of unsupervised learning because we are feeding in some features, which, for example, the colors of the image, the labels on the page, and so on. And we are getting back other features like which images go with each images, what group they belong to, and so on. It's not really trying to predict some target value because we don't have that target value at the beginning, but it's transforming the features that we gave into something that we may find more useful, like in which group the image will be placed. So basically, we have feature values, the learning system, and it will produce new feature values. And this is unsupervised learning because we are not controlling during the learning process exactly how the system is learning by comparing to some target value. We don't have that target value in this case. So in this case, we say that the data is unlabeled, or the data may be labeled, but we are not using the labels. We are only using the features, and we want to find some structure in the features. So this allows us to obtain new features that can be used either by themselves because they are useful, for example, which cluster the image belongs to, or they can be a step in longer learning tasks, for example, extracting features from images, pre-processing, things like that, so that then we can use them in other kinds of learning tasks. Another type of machine learning problem is supervised learning. We are going to start by looking at these problems, and in this case, we call it supervised because for each example that we're going to feed into the learning system, we also know what the correct answer should be, or what we would expect the system to give us as an answer. So we have the data, which has target values and feature values corresponding for the same examples. We feed the feature values to the learner. So the feature values are those things we expect to find in future examples. For example, if we were dealing with this kind of problem with identifying handwritten digits, the features would be all the data in the image itself. Because these would be, the new examples would be just an image with handwritten digits. The labels are those that we added so that we know the correct answer. And these are not fed into the learning system itself from the beginning, but they are used to measure the error between what the system is telling us and what the system should be telling us for each particular example. So this way we can supervise the learning process and measure at each instant the performance of the system by comparing the output of the system with the target labels, the target values that we have. So this will be fed into the learning system so it can learn to reduce this error and match its output to the desired values. Now here we can distinguish two different types of supervised learning problems. When we're trying to predict continuous values, we call this a regression problem. If we're trying to predict discrete classes, we call it a classification problem. An example of classification, for example, would be face identification. So this system can scan an image and classify each region either as face or not face. So it can cover different parts of the image and identify where the faces appear. Now here you can see, for example, this woman has her head is slightly leaning to the side, so the system failed to identify this as a face. It seems to be specialized on faces that are vertical and not diagonal. So this is an example of classification with supervised learning because we can use a set of images where we know what the faces are, or we can use a set of faces and measure the error of what the system is telling us about each region in the image, and thus supervise the learning process by measuring these mistakes and trying to minimize them. In reinforcement learning, we have something that is similar to supervised learning in the sense that we have some feedback about what the system is doing, but the feedback is not direct. It's not for each example. So an example of this would be autonomous driving. You are training a system, a computer, to drive an automobile, and if the computer turns the car incorrectly, a few seconds later or a minute later or something like that, it may hit a tree. So you know that something went wrong when you hit the tree, but now you have to figure out when was the incorrect decision taken. So how can we use the output with this critic that evaluates if things are going wrong or right and feed it back into the learner. So this is similar in some sense to supervised learning. We have a way to find out if things went wrong or right, but we don't have the immediate label for each example, for each instance, and we need to use different techniques for this kind of learning. We are not going to cover this, so in this course we are going to cover these two, unsupervised and supervised learning, reinforcement learning. There will be another course next semester where we'll cover a bit this, but for this one we'll cover the basics, supervised and unsupervised learning. So there are many examples of reinforcement learning, like playing games, driving cars, controlling robots, and things like that. And the idea here is that the system needs to learn to make the correct decisions, but the feedback on mistakes may be delayed with respect to the decisions made. So you may make a wrong move in chess, but only lose the game after 5 or 6 turns or something like that because of that wrong move. And that is the challenge here in reinforcement learning. Then you have mixtures of this. For example, semi-supervised learning. You can use mostly unlabeled data, because typically unlabeled data is much cheaper, easier to find. For example, if you want to train a system to identify images of cats, you can easily download many images from the internet. But if you want to have labeled data where it says this is a cat, this is not a cat, then that takes some extra work, because you need someone to label that data and create that data set. With semi-supervised learning, we can use unsupervised learning techniques to try to group things together that are similar, or approaches like that, and then help us learn even if the labeled data is a smaller set, because now we can also rely on unlabeled data due to similarity to examples that we have labels and so on. So there are many different approaches here as we go into the details, but these would be the 4 basic kinds. And in this course we will cover, we will focus on the main ones, supervised and unsupervised learning, because this is basically a big difference between trying to predict something that we have in our data, or trying to find structure in our data so that we can extract some information from the features that we have and how they are related to one another. So the goals for this course is basically to give you an understanding of the foundations of machine learning problems, methods, algorithms, and so on. So you understand the basic concepts and how these things work. Give you some experience with these techniques and applications, how to use machine learning to solve practical problems, and also learn to understand the literature. This is an important aspect, because if you want to proceed or deepen your knowledge of machine learning, you need to understand the papers, the books, and so forth. And for that, you need to be a bit familiarized with the mathematic notations, formulations, and the kind of language, so to speak, that you'll find in this area, because machine learning is very strongly related to probabilities and statistics, and has a lot of formal language from those areas. So we will cover a bit that part. I will show you lots of mathematical formulas. The idea is not that you memorize or learn how to demonstrate the different deductions, things like that. That's not the purpose. The purpose is that you learn to read them, so that when you go read a paper on machine learning, you don't get stuck just because there are some formulas there. So we'll start with this introduction and supervised learning. This will be about half the semester for supervised learning. Then we will cover these aspects, regression and classification. Mostly we'll start with regression because there are some simpler examples, and then we'll look at classification and look at some different methods for classification. Then in the second half of the semester, we will take a look at theory of machine learning. This comes after supervised learning, because after you have some intuitive understanding of how these things work, the theoretical aspects are easier to understand. And then at the end of the semester, we will see unsupervised learning. So things like manifold learning, feature extraction, and especially clustering. That will be most lectures for unsupervised learning will be on clustering. Okay, so to sum up this first part, before we take a break, the idea of machine learning is that we can automate the process of learning from examples without having to make up explicit rules to tell the computer what to do. So the computer will learn how to solve a problem just by looking at the examples we give it. We saw these concepts, the hypothesis class, which is the class of all hypotheses from which we are going to try to find the best one when our system is learning. We have the model. The model is a representation of the hypothesis class, typically using parameters so that we can adjust the parameters and cover the hypothesis class by changing these parameters. And then the hypothesis, which is each instantiation of those parameters. So what we're trying to do is find the best hypothesis to solve our problem. Inductive bias, we're going to see more of this by the middle of the semester a bit more formally, but it's the idea that we need to constrain the set of hypotheses that we're going to consider so that we can extrapolate from the data that we already know to something that we still don't know and want to predict. So without that kind of constraint, we cannot do predictions outside the data that we already know. And then we saw different types of machine learning problems. So aside from the slides and the lecture notes about this chapter, I'll recommend that you take a look at these parts of so the Alpaiden's book, chapter 1, Mitchell's chapter 1, and these sections of Marsland's book. They all cover these parts, what machine learning is, different kinds of problems, and so forth. So let's take a short break and we'll continue at 16:50. So 10 minutes to 5, we will start again.